Good afternoon, dear participants. Good afternoon. Arshdeep Singh, good afternoon. Hello, sir. Hello, am I audible?
Audible, sir. You are audible.
Yeah, thank you. Arshdeep Singh, sir, are you there? Arshdeep, sir, are you there? Dear all, please wait. I'll connect with the today's speaker. I think he's facing some issues. Just be. Hello, good afternoon, sir. Arshdeep, sir.
Uh, am I audible? My screen is
Yes.
with.
Yes, sir. Yes, sir. Your screen is visible.
Okay. So, welcome everyone. In previous two sessions, we have seen what is ROS, why we need its philosophy, history. Then we moved on to Linux, Ubuntu, and see the basic Linux commands, why we work with Linux, and what is the difference between graphical interface and command line interface. So yesterday we have tried multiple commands related to file manipulation and moving into the directories, and learned some information about important directories, what type of information they hold. Apart from that, there are another two major commands, sudo and source, that we will encounter in ROS and Linux very often. Sudo means super user. In Linux, the user does not have all the permissions. Like in Windows, there are some folders that we can't open, or there are some files that are protected by the OS. Similarly, in Linux, there are some files uh, that doesn't for that user that does not have the permission to do changes. For that, we use command sudo. Sudo means super user. Like we get the privilege of the root. We can perform some OS level tasks. Apart from that, there are some permissions related to the files and related to some operations. We can also perform some operations using sudo. We will see this how sudo works. And the second command is source. We have seen about terminal, shell, and uh, prompt and command. Whenever we open a terminal like this, I have opened terminal. So there is one shell session running. By default, in Ubuntu, we use bash as an shell. So our bash files will be denoted with extension dot bash
Excuse
or
me, sir.
dot bash RC. जी sir.
हेलो सर. हाँ, आपका
Yes sir.
थोड़ा लैग हो रहा है. I think if you can turn off your video and then.
Okay, okay, okay.
हाँ.
So if some it happens again, then let me know. I
Yes,
think
yes,
there is
yes.
some internet issue from my side.
हाँ. Yes, yes, yes.
So I was talking about the bash shell. Bash shell has basically files with the extension of .bash. Uh, Whenever a new shell is opened, a bash script runs behind it. What a bash script is a file containing multiple commands. Why it is needed? Because it has to set up some environment variables, some paths, because it is our way to interact with the OS, and further OS will interact with the hardware. So now we will see how source is useful when we're trying to use ROS. I will demonstrate these both commands in upcoming time. Apart from that, as I told earlier, there are permissions. So in Linux, basically there are three permissions for each file folder. These are read, write, and execute. Like uh, in Linux, why do we have these sort of permission structure? Because Linux is also used in servers, and in servers there are multiple users. Like if I have created a file, then I will decide that other users can access that file or not. So this is the basic purpose of these permissions. Similarly, there are three types of classes with which we can assign permissions. There is owner, means user who is creating the file. Then there is group. User who created the file can decide how many users or this user can access my file and in which permission type. Like another, the users in this group can read this file, users in this group can write this file, and third class is others. In others, everyone that has access to the server can use this file. So I'm going to demonstrate this permissions how it works. So let's just go to our documents directory and create a file named online.txt. File has been created. So yesterday we see a list command and list command with arguments, and we were seeing WX, and I told that we will discuss it for in next session. So today we will be seeing that what this RWX was meant for. So you can see RWXR, what does mean? This means the permissions R read, W write, X execute. So this is divided into three classes. The first three letters from R denotes for the user group, another three are for the group only, and then remaining three are for the others. So I have created the file online.txt. Let's see where it is. Here is my online.txt. Currently it is just text file, so it will not have execution permissions when I have created it. So I created this file. Now I have permissions of read and write. Then for a group of users who will log into this system will have permissions of read and write. Then another others have only permission to read it. So let's go to graphical interface and see the file. How does it look like there in the folder? Because it will change when I am going to change the permissions. So this is my file online.txt and it is showing as a normal file. So let's change the permissions for this file. For changing the permissions, we will use one command chmod, which means command modification. So let's say I am the user and I want to remove permissions, my permissions for this file, so that I become unable to open this file. So as a user, U denotes user, so first will be user. Now I want to remove command, remove permission. So for removal, I will be using the sign of minus, and if I was giving permission, then I will be using the plus sign. So what I currently have two permissions, read and write. I want to remove them. So this is the command. Now for which file? My file name is online.txt. So let's see does what changes come in while listing the files. You can see the permissions for the user group have been removed. Let's see how does it look like in graphical interface. You can see there is a lock and there is a cross, which means I didn't have permission to access these files. You can see you don't have permissions necessary to open the file. So while using ROS, you will encounter with this problem of uh, you don't have permission to access this, or you don't have permission to open this file. So let's, as I told earlier, there is super user sudo. So let's try to open this file using sudo. Every time you type sudo, a password which you use to log in to the system will be required. As I was trying to open the file using VS Code, and I am getting some warning from the system that you should not start VS Code as a super user. So Linux has multiple security levels, and we have to respect them. So we have another type of file editors available. We can open this file with them also. Let's try. There is another file editor available from the genome, that is Gedit. Let's try to open this file using Gedit. So you can see the file is opening now. Let's type something. The interface is a little bit different. Uh, I need to change the font colors. It is currently in the white color, so it was not that much visible. Let's save this file. So the file has been saved. Now, when I tried to open the file without sudo, I got that I don't have permissions. But when I use sudo, I got the permission. So when you don't have permissions, you can try with sudo. And when you are not the user and your file is accessible to others, then you can set the permissions. Let's uh, reassign the permissions so that you can understand how to give permissions also. We will use same command chmod for the user using u. Plus sign means I am giving permission. Let's this time give permissions of read, write, and execute. So every time you do something wrong with the commands, there will be some output. So what this output saying? Missing operand. So what does it mean? That you have typed a command, but on which file or which directory you want to implement that command, you are not useful. When you start your learning journey, it will make debugging much easier. So the now commands have been modified. Let's see on the graphical interface. You can see the file becomes normal. There is no lock or cross showing that we can not access this file. So this is about the permissions, sudo, super user. Now in let's discuss about how do we install softwares. In Windows we have our Microsoft Store, from which we can install multiple softwares. Apart from that, we can just go to that particular software's website and use .exe, download .exe, and we just have to install it. That simple process. But in Linux, it is little bit different. So as Ubuntu is based on apt, so there is one way of installing softwares is apt. Apt is repository based, so it will access the packages holded on GitHub repositories and will accept those repositories for updating the softwares, for downloading the softwares and finding new list of softwares. Another option is Snap. Snap is managed by Canonical, who maintains Ubuntu, and Snap Store is available with us as an like Windows Store. So this is Snap Store with the A sign. So you can see there are multiple softwares available in Snap Store. We can even update our pre-installed softwares also. So for the new user, simplest way is to just open the Snap Store and check if their required software is available or not. Let's go to VS Code. I already have installed VS Code. Like if new users want to install VS Code, one way of installing is using Snap Store. They can go to Snap Store and install it. What are the another options? Another options, as APT is the main package manager, we can use APT. So how do we use APT? APT is a command to access the package manager. Let's see, right? APT and help to see what does APT offer. So APT is a command line package manager and provides commands for searching and managing as well as querying information about packages. So what are the sub commands of APT is list, search, show, install, reinstall, remove, update, upgrade. So we will use update, upgrade, install and remove commands most of the times with APT. Whenever we are trying opening our system, as it is not an store that we will going to get notification that these updates are available. If we are going to install something with APT, the first process is to update the repositories. For that we use APT update. Let's try APT update. It will go to the repositories and check if any changes in the repositories are there, so that we can try to compare with pre-installed softwares, and if there is update, then it will mention that these updates are available. So we get some errors, some two errors, some warnings. And what does they saying? Permission denied. And we just learned that if we don't have permission, we can use the power of root user, super user, and for that we use sudo. Let's try this with sudo apt update. Now you can see it is going to repos, different websites, and trying to fetch the data, reading package list, reading information, so and giving output. 8 packages can be upgraded. So we can use apt to install some softwares, and while installing ROS, we mostly use apt. It is the easiest way. We use just sudo apt install and then the name of the package we want to install. Let's try how uh, how does we know that if the package is available on the apt or not. Then we can use apt search, apt list to check. Another thing is to go on their official website. Let's go to official website of VS Code, as VS Code is available in Snap Store also. Let's see how they recommend or telling us to install on this Linux system. So whenever you see Linux, then there will be mainly two package managers. One will be Debian type, another is RPM. As our Ubuntu is Debian, so we will going to use this Debian. So a Debian package is starting to download. Now, how we will install it? Can we just double click it on the package and get it installed? There is two ways of installing this downloaded Debian package. One is using Snap Store, another is using APT. And for APT, there will be documentation. Every software provides documentation for installation on the Linux systems, because it is a little bit tricky. So you can see install VS Code on Linux, Debian and Ubuntu based distributions. So they have mentioned each step, how to install it, what issues you can face, and how to maintain it. So simply they are telling first to download the Debian package, then go to your downloaded directory and use apt install and file name. So you can refer official websites if you want to install something. Another method that I was telling was using the Snap Store. Let's see how does it look like. So I have already downloaded this Debian package for VS Code. When you try to open it, then you will have option of opening it with software install. This software install will get you to the Snap Store, and there after some processing you will get the options to install it. Here I already had installed it, so it is showing that it is already installed. Otherwise you will get just simple option of install and it becomes very easy to install. So this is about the package installing. Why I told you this? Because new users face issues while installing the software, installing ROS. So, and this is about all about the basics of Linux, basic commands. Now I am going to move with the ROS, basic ROS commands, and will understand the basic commands given by the ROS. As we have already familiar with the terminal, shell, prompt, and command, and we have already seen some basic Linux commands. So let's move on to using ROS2 commands. Before using ROS2 commands, the first thing to do is set up the environment. Before starting this, I will uh, point you to official documentation of ROS2 Humble. So if you ever got some problem, then you can refer this documentation. It is not great, but it is good documentation. So you can start the installation and some basic tutorials and basic information. So it documentation also covers the command line tools that I am going to cover. So the first step is configuring environment. I am going to paste this link in the chat box so you can refer it later. And so the first step is configuring environment as per official documentation. Now they will not mention why we need to do this. From our understanding, we understand that ROS is based on another operating system, which is Linux-based operating system. And we also understand that we use terminal, we use shell, and when we open new shell, there is a bash script that runs behind it. Now, ROS is not a normal software, not a normal library. It is not like that there is a graphical interface where I am just going to like search ROS and there will be software and I will just double click to open it. No, there is only directories. There is no graphical interface or graphical software. So how do we start or use ROS? We have to use command line only. And for command line, using on command line, we have installed ROS. How this shell will know that this system has an ROS or this system user wants to use ROS. So for us to use ROS, we must have to configure something. And for configuring, ROS provides us a bash file, setup bash file. So before starting using ROS, our purpose is to source this file. As I told earlier, using source, we run bash files which have multiple commands. So first, let's see, as I told earlier, what is OPT optional directory. Let's go to this directory and see this setup.bash file. As I told you earlier, there is only one main directory which is root. So let's go to root and then we will move to optional directory. Let's move to optional directory. Then where we want to go? We want to go to ROS directory. Then we want to go to humble directory. Let's see what it holds. So it holds some further directories and some files. It has some bash scripts. So let's open this setup.bash and see what is inside it. So you don't have to worry what they have written in the bash file. This is part of bash scripting. We are just going to use this file. Why we are doing so? Because we want that our shell session must understand where is my ROS libraries. If a user is trying to use ROS commands, then shell should be able to find what that command means, what that command wants to interact with. So simple funda is to source this setup.bash file. So I am going to source this file. If you will not store this file, then the ROS command line will not be available to you. So after that, let's begin with the command line of the ROS. So the major basic command is ROS2. Let's type ROS2 and help. So what is ROS2 command? ROS2 is an extensible command line tool for ROS2. So what offers? It offers us many sub commands. We already know ROS has an architecture based on nodes, and nodes can communicate with the help of topics, services, and actions. So also we have just recently discussed about the packages, and we install packages with the help of apt. So if you see clearly, there is an subcommand package, there is subcommand topic, there is subcommand service, there is subcommand action, there is subcommand node. So we are going to use these commands to understand how does ROS command line works. So if we want to use these commands, then there must be some packages, some nodes on the system. So for that we need to install some pre-built software, pre-built package before jumping to writing your packages yourself. So one popular package is TurtleSim. So we are going to install TurtleSim. For installing TurtleSim, you can refer to official documents. There they have mentioned how to install it. Let's just copy their given command and install the TurtleSim. The first command is apt update, then apt install. Then we are mentioning that we need this package. You can copy paste multiple commands. Terminal will understand that these commands are different and will execute in the order itself. So it is now connecting to the different repos and finding the package. So as I already have installed this package, so I am getting ROS Humble TurtleSim is already the newest version. If you don't have this package on the system, then it will simply install. So we just installed a package and we know ROS2 command line has an one command package. Let's see what does package command offer. It has basically some subcommands like create, executables, list, prefix, XML. So just list the available packages, ROS packages on my system. As I am frequent user, I will have a long list of ROS packages. You can see there is my long list of ROS packages. If you want to check that if your package got installed correctly or not, then you can use ROS2 package list and grab your package name. Like we just installed Turtle Sim. Then you are getting output of Turtle Sim means you have successfully installed this package. Now let's see what other subcommands package command offers. Then there is executables. Executables means what nodes this package holds that we can run. So let's type this ROS2 package executables and we need to package name. Let's type turtle sim. So this package holds four nodes, four executables. You can refer to documentation also. In documentation, they already told that these nodes are available, and if you are little bit advanced user, then you can see their code and you can understand how many nodes this package holds, and you can see their code also, which we will see in the next upcoming sessions. So this package has four nodes. Now, how do we run nodes? Does ROS2 offer any command? Let's check. So there is a command run. Run a package specific executable. We just installed a package, TurtleSim. We just checked what executables this package offers. We have the list of executables. Now let's try to run a node. We understood that there is ROS2. Then it holds subcommand run. Now how do we know what we need to enter further? We always use help. So after run, what it needs package name, executable name. To run a node, we need the package name in which that node is suited, then the name of the node. We have just checked that our package name is TurtleSim and we got the list of the executables available. So let's try to run one node. Let's run turtlesim underscore node. So you get a small window and a small turtle in that. So this is a first ROS node. So it is giving some information on the turtle sim also, on the terminal also, that a node named TurtleSim has been started, then a turtle has been swapped at this position and this orientation. So it is mentioning the coordinates of this window that at x 5.5 and y 5.5 this TurtleSim is going to be present and with orientation also. So now we just got into the packages, how to install it, very basic command line of the ROS, how to run a node, how to check if a package holds how much nodes. Now, It is all the command line interface. Is there any graphical interface also? Yes, there is a graphical interface also which helps to understand how nodes are communicating, on which topics they are communicating, what services are available. So that graphical interface is known as RQT. So as we just installed Turtle Sim, now we will install RQT. So RQT is just a graphical interface based development for ROS. So we are just using apt to install RQT. You can refer to official document also to install the RQT. So I am just going to copy these commands from the official documentation and going to install RQT. So they will ask sometimes for the permissions while you installing some software. Then you need to according to your need, you need to grant them access by mentioning yes or no. So it is now downloading the package, then it will install the package. So it will take some time to install and become available. So until that, like this is one terminal window. We can have multiple tabs of this terminal. I can go to new tab. Now new shell has been opened. If I am going to open new shell, then it is going to run its new bash script. And we already seen that for running ROS, we need to source the script of the setup script of the ROS. So are we going to just every time if we are going to open new shell and we need to open multiple shells to understand because it is all just command line interface. So is there a fix? Yes. As we are going to open shell, there is a file that will be executed automatically and it is a bash file, so we can add some commands to that bash file. What command? Our source command for sourcing ROS setup file. So let's see what this file that this shell executes every time a shell is opened. So this is the bash file. It set up everything in the shell. So we just need to add our command. How do we can add this command? Just open this file. You can edit this file if you know what you are doing. Now I just have to add one file, add one command, then I am going to add one command. So as I already added this command, so let's, and this file has been already executed. So let's see if ROS commands are available or not. Let's type ROS2 and enter. I am getting the help related to this command, which means this command gets executed. Means ROS functionality is available. So you like need to get some knowledge about the bash scripts, so you can do some little modifications. Even if you are doing something and you are typing 10 commands, then you can just write these 10 commands in a bash file and you can save this file and you can just run one file to run multiple commands. So let's see if our RQT package, it is currently being installed. So Why we are using this turtle sim? We are using this turtle sim to understand if we are going to run a node, then how does it look like? As we already seen about the topics and publisher and subscribers, so we are just trying to understand command line and how does it look like. So let's again go to ROS2 command, and as we will start from the node, then we will move to topics, then we move to services, and then we move to action. So let's understand what does this node command has. Let's just type ROS2 node and help. So it has basically two subcommands, info and list. Info means information, some about a node. What information? We will just type and see. Then there is list. List means which nodes are currently available or working. Let's type ROS2 node list. I'm getting nothing because I have not executed any node. I executed one node and I exited that node. So let's open new tab and run the turtle sim node that we ran sometime before turtle sim. And in Linux you can use the comfort of double tab. If I just press the tab two times, then I get some options. It is like auto completing my commands or showing me the options which are available. So it is just showing me the options, like my run command is for running nodes and it is showing me four options that I can run any one of these node. So let's just use our tab to complete this and just run it. So this by this way we just started one node. Now let's see what does this command return. You can see we got one node turtle sim that we just executed. So let's see the information about this node. Now we need to type the node name, whose information we want to see, and our node name is turtle sim. So what we are getting? We are getting subscriber, publishers, service servers, service clients, action servers, action clients. It does not mean that all these are active now. It simply means that this node can do all of this, but it is not mandatory that these will be active now. So let's understand them one by one. Subscribers. So this node is subscribing on these topics, and this is the message type which is being transmitted, which is being shared on those topics. Similarly, there is publishers. So this node is publishing on these topics. Then this node offers these services. Currently, there is no client, no one is requesting services from this node. That's why there is no clients. Similarly, this node offers just one action. So it is available here and no one is requesting that action. So it is empty. In the upcoming session, we will working with services and action clients, and we will just call services, call actions, and you can see that there will be clients for both service and actions, and will compare both service type of communication and action type of communication, and we'll see how does it actually look like on the system. We will use RQT, graphical interface, and command line interface both for understanding this. Now we just have seen how to run a node, how to check if a package has a node or not, and we just seen how to source a ROS environment, how to split terminal, how to run multiple commands. So let's, our RQT has been installed, and RQT is a ROS package. So let's see what executables this package holds. And for that, I am going to use the command line given by ROS2 package executables, and my package name is RQT. So does this have some executables? No. Why? For that, we need to look up on the RQT documentation, because RQT is a big graphical package. It offers multiple things. So I'm just going to run it, run one of the packages, RQT graph and RQT graph. You can see this is the interface of the RQT graph. Now you may have question that why it does not return something, because RQT is not a simple package. It is meta package. What does meta package means? It includes multiple sub packages, and one of the sub packages is RQT graph. If I just run RQT, then you can see this is the default RQT interface, and it offers multiple things. It offers service, topic, visualization, actions, and multiple things. And at the beginner level, we don't want to just go into that much complexity. We are going to use a sub package of RQT, which is RQT graph, to see which nodes are active and on which topics they are communicating. So I will just run the sub package RQT graph and see how does it, what does it offer. So currently we have ran only one node, and if there is one node, then it will not be communicating with some another node, because for communication there must be some person on the second end, there must be some node on the other end. So there is currently no node. So we are getting only one node, turtle sim. This ellipse means this is node, and there will be rectangles mentioning about the topics. So to see how it look like when there is multiple nodes, so let's just open a new tab and run another node from turtle sim package. ROS to run turtle sim. Let's run this tally of key node. So it is giving some output to us. Use arrow keys to move the turtle. So let's see if it works or not. It is like small turtle, difficult to visualize. I am just pressing the up arrow key. You can see it is tracking some path. It is rotating as per my inputs from the keyboard. So this is a node which offers an interactive way to manipulate something in the node. So we had one package we had one node just to open a graphical interface. Then there is another node which is responsible for manipulating that. As per the architecture of the ROS, we have seen that node is responsible to doing some particular task. So we can verify that from this. In a package, there are multiple nodes performing multiple tasks. Now, let's see, there are now two nodes. How does RQT look like? There is no update because we opened RQT before running the second node. So we have to refresh it. There is a small refresh button. You can refresh it. Now, we just ran two nodes. One is turtle and another name tally of turtle. So, as I said earlier, these ovals represents nodes and this rectangles represents topics. So, this turtle node is publishing data on this topic and it is being subscribed by tally of turtle node. Similarly, there is another topic on which turtle is publishing data and tally of is receiving. And there is another topic, command velocity, on which tally of turtle is publishing and turtle sim node is receiving. Let's see on the command line what does ROS2 node info will return for this tally of turtle node. ROS2 node info of which node? Tally of turtle. You can see it subscribes this parameter events and it publishes data on these three topics, like it can publish, and RQT shows only the active topics that are currently being subscribed by a node or currently being published by a node. So you can see in publisher there is one publisher, command velocity, and you can see in RQT that is available here. Now there is service and action. We will discuss these when we are going to discuss service and action related commands, and we'll see how does it vary. Now, how to kill a command, how to stop a node. Is there any particular kill command or how do we do that? For killing a node, we can just use Control plus C. I am just pressing C and you can see I am back to my prompt. My node just got killed. We just exit that node. Let's check from the ROS2 node list how many active nodes are there. You can see there are only two nodes, TurtleSim and RQT. Although RQT is a graphical interface, but how did we run it? We ran it using ROS2 run, then package name, command name. So that's why this node is also present here. Let's check the info for this node also, ROS2 node info, and we can just copy paste the name of this node, and you can see this node is has not subscribing to anything. It has publisher and it is has services. We don't have need to go to depth for this node because it is designed for graphical interface. It has complex systems behind it. So we can check information about any running node using ROS2 node info. We can see which nodes are active using ROS2 node list. We can use RQT to check the communication that is being happening in the graphical interface. So this is so today we have seen how to install packages, how to use sudo, how to use source, how to start with ROS. Uh, First command from the ROS2. Then we see how to install ROS packages using apt, how to use package command. Then we see how to check if a package has an executables or not. Then how to run that executables. How does node look like in graphical interface, in command line interface? What are the basic commands related to the nodes? So after this, in the next session, there are some pending commands from the ROS2 related to topics, services, actions, parameters. So tomorrow we will be discussing about topics, then service, then parameters, and then action. And for that we will be using this turtle sim package, and we will see some changes in this graphical interface by calling a service, by changing a parameter, and by executing an action. So that is all for today from my side. So if you have any query, you can just ask, and I just pasted the a link for the documentation. You can always refer to that documentation, and if you have like certain demand, or you want that just show us some simulation or that sort of anything in your mind, just let me know. So that's all for today.
Yeah. Thank you for the nice session, sir. Dear participant, if you have any queries, please feel free to ask. Yeah, this is again a hands-on session. If you are doing the things, then you'll get some queries. Yes, anyone?
So if no queries, then let's meet tomorrow. uh, yeah, there is one query. Yes, a node can act as publisher and subscriber as well. A node can be anything. It can publish data to 100 topics, and same time it can get data from 1,000 topics. So it is possible to have publisher and subscriber in one node only. As I just showed the like ROS2 node info, there was subscribers and publishers both in that description. So it is possible. So any another query if anyone wants to ask anything. For the gazebo sessions, I have just two sessions remaining. So it is on you. If you want that I introduce gazebo first, then I can do that after completing this basic command line. And like you have just two options for the two sessions. Either I just introduce to the package structure, how do we write node, how does this ROS2 packages look like, what are the uh, things that required when we are going to write packages by ourselves. And then there is second option where we I just introduce you to gazebo, how does it work, and what options, what are the things that gazebo offer, and what we can do with the gazebo. So it is on you. You can uh, tell me if you want to know more about package structures or more about simulation. Uh, can we prefer to go with virtual environment for setting the ROS2 for first time? If you are using Linux, then there is no need for virtual environment because it is not like Python. Like we need to set up a virtual environment or do something like that. It has its own package managers like Ament, CMake, Ament, Python. So we don't need to go for the virtual environment. No need to set up a virtual environment for ROS2. It will directly interact with the Linux environment and you will not face any issues. So one student is asking to start with simulations. So if all others, if majority is asking for simulation, then I will introduce Gazebo in the next session itself. So if it is all are agreeing with the with to start with simulations, then please let me know. Currently, only one student is mentioning about simulation. So,
Yes, sir. We'll let you know by tomorrow's session.
हाँ, okay, okay.
टुडे सर हम आज ही बता देते सर इट विल बेटर टू बिकॉज
There is another query, TF and TF2. Basically, there are two versions of ROS, ROS1 and ROS2. So, for the handling the transformations, there are two libraries, TF and TF2. TF is for ROS1, which is end of life. We don't use it anymore now. And TF2 is for ROS2. You can see the documentation also. It is in the intermediate level. So you can see what does TF2 library do and how do we use it to write a scripts and how to do things using the transformation tools. It basically handles basic transformations. For simply TF2 is for ROS2 and TF is for ROS1. And in vision based applications, we deal with transformations from camera to word, camera to robot, camera to object. So that's all. So thank you everyone for this session. So let me know about the. Yes, we can integrate OpenCV and using ROS. Uh, when we use like Intel camera or any camera, maybe RGBD camera, depth camera, when we want to use it with ROS, then the camera manufacturer provides us with an package. As just I installed TurtleSim package, and if I want to use some hardware, then that hardware provider will provide me with an package. That package will be holding all the necessary things that I need to use that hardware. What it will include, it will have its basic firmware, basic communication setup at the embedded level, and it will provide me some nodes to run. If I am connecting my camera, then if it is Intel camera, then there will be a package and I just have to run few nodes and the topics will become available, and in these topics I can see the data in visual way also, in command line way also. So, and if I am getting that, then further upon I can use the OpenCV. OpenCV is also available for ROS and I can integrate it in my nodes and I can do processing in real time itself. So any another query?
Yes, Mayur sir.
नो सर थैंक यू अर्शदीप सर
So you are not audible.
एम ऑडिबल टू यू सर
No, sir.
सर देन कंक्लूड द सेशन सर कंक्लूड करून टाका
Okay. I think he's facing some issues. So let's wind up today's session here. So tomorrow again we'll start at the same time. But today also we have another session. So dear participant, do not leave the meeting. Thank you, sir. Thank you, Arshdeep, sir,
Okay, sir.
for the excellent interactive session. Yes.
Thank you so much, sir. Thank you, Ashif, sir. Am I audible, sir?
Yes, a bit.
So next section, just a minute.
Mahir sir, you are mute.
Okay, am I audible to you, sir? No? I think so something. I will do the meeting again.
Sir, Pratik sir, am I audible?
Yes, sir. You are audible, sir.
Am I audible to you, sir? Hello?
Sir, please hold that mic nearer to.
Hello? Am I audible to you, sir?
Yes, sir, you are audible.
Okay, thank you. Just a minute. Hello, participants. Our next expert is Dr. Santa Kumar, sir. He's from the IIT Palakkad and is very renowned in mechanics of the robotics. Will explain you kinematics, dynamics, and the control of the mechanics. So he will join soon. I will wait for the 5 minutes. Okay. So do not leave this meeting. Yes.
Hello. Good afternoon, sir. Santa Kumar sir, are you there?
I think so. He has not joined today. I will wait for I just call him. Just I think Ganesh sir. I don't think so. He has joined it. Just wait. I'm just calling him.
Good afternoon. Can you hear me?
Yes, sir. Yes, sir.
Yeah, earlier I had some problem with my network maybe.
Okay.
So I
Very
could
good
not hear
afternoon,
it.
sir.
Yeah, very good afternoon.
Uh, Dear participants, our next section is about to start, and Dr. Santa Kumar sir has also joined the session. I'll just brief about Dr. Santa Kumar Mohan sir. Sir is a renowned personality in the field of robotics and control. Sir has completed his PhD in robotics and control from IIT Madras in 2010, and he has served as assistant professor in mechanical engineering department at NIT Calicut from 2010 to 2011. Sir has also worked as a postdoctoral fellow at the Korean Advanced Institution of Science and Technology, Republic of Korea. In 2012, Sir has joined as the Faculty of Mechanical Engineering at IIT Indore, and he has also served at various renowned institutions like ISC Bangalore and various abroad countries also like Russia, Republic of Korea, Germany, and France. Sir is having his active research areas, which includes service and field robots, parallel robotic platforms, and assistive rehabilitation robots. Sir has received Outstanding Young Scientist Award for the year of 2014 from Korea Robotics Society. Sir has also received various fellowships, such as European Master on Advanced Robotics Plus in the year of 2018-19. Then Alexander von Humboldt Fellowship 2016 to 17. Then Satellite Across Virtual Institutes Savi Fellowship in 2013-14. World Class University Fellowship in 2011-12. Then Brian Korean 21 Fellowship in 2011. Sir has published more than 150 research papers in various reputed journals and conference proceedings. He is also author of one book. Sir has edited four different books, completed 15 externally funded projects, and currently Sir is having ongoing 5 sponsored projects. Sir has also associated with various international reputed journals as a technical editors. Sir is also adjunct professor at Department of Mechanical Engineering Design uh, at IIT Madras and faculty fellow at IIT Palakkad University iHub Foundation. Sir is a founder director of IIT Palakkad University iHub Foundation and Technology Innovation Foundation of IIT Palakkad. So through this brief introduction, you might have known about Sir's biodata. Sir is very good with robotics and control, and we are fortunate enough to get Sir as a uh, resource person for this particular session. Now I request Dr. Santakumar Mohan sir to uh, start with the session. Over to you, sir.
Yeah, thank you. Thank you for the long introduction and as well as welcoming me. First of all, thank you, Mayur, for inviting me to talk this particular session. Mayur mentioned that there are many things would be covered in this particular short-term program. So I'll be talking mechanics part. So I'll just give like essence of mechanics, why we need and how we can actually move on and as well as I'll be giving an idea how to actually like realize the system before you fabricate. That is what the whole idea behind this particular course, which I think. So even he said that ROS would be covered by one of our friend Jayant. So and he also would be giving a real-time session with his own lab. So I'll be talking the uncovered part, which is the mechanics part. So I hope that would be fine, then I will actually like start sharing my screen.
Yes.
Then you can actually like, yes, yeah. So I'll just start sharing my screen. I'll share the screen. Okay, I hope you are able to see my screen. Yes, right? Yeah.
Yes, sir. Visible.
So I'll just talk about different things first. You see, like I come across robotics background since 2000. So when I was a second year student, since then I'm working in robotics. So you can assume that around 20 plus years I am working in this field. I found there are certain things which we need to know. That is what important in the modern days. So that I just to put it in a different perspective here. So for example, if you think about a robotic engineer or even a design engineer, so there are certain things you need to fulfill, right? So imagine any engineer, the task to be completed is the bigger concern, right? Even a teacher, so you have to go and complete the syllabus and make sure that every student supposed to be get understand what you are trying to teach and they excel in their career, right? The same way when the robotic engineer, the task to be completed, that would be given to us, right? When you talk about robotic engineer, the task to be completed, you have to use with the help of robots. That means, so you are thinking about the robot, which is the practical system, which is I am putting as a real system. The real system would be doing the task to complete, right? So, but I put the slide in such a way that you can see task is one side, which is I put in a red color, and the real system, which is what we are talking about robot, that is actually like on another side, which is green, right? So we need to see how to bridge these two. For example, I want to make a robotic assembly. Okay, so I have to choose a robot from the industry catalog, which is on shelf, or I have to build my own robot to fulfill the assembly task, right? So that means task to be completed is assembly, but I need to come up with a system which is practically in this case is the robotic manipulator or robotic system, which is supposed to be put in place so that the task to be completed. But you look at it here, there is a big gap, right? So the task and the real system is in the big gap. So when you go deep down, so we need to fill this gap when we go deeper. So when I say task, so the task would be giving some user input. For example, you are in a industry, you are an engineer, or you are a teacher. So some user would have been given. For example, you are a teacher. So the principal or probably director of the institute say that, so I need so and so things from the students. So you please do so and so things to fulfill this, right? So that means some user input would be given. The same way in industry, we will take the same example which we said the robotic assembly. The user say that the user indirectly the manufacturer or the industrialist, he said that you see currently my assembly task done by manual. Okay, so the manual labor is doing 1,000 parts in a day. So I want a system to be completed in a day with the help of robot, and I'll be giving a space of 1 meter cube, and the fund is actually like limited this much. So you come up with the solution. Okay, so now you can see that the user is throwing something, right? From there, what we can do it, we can derive some kind of specifications, which is what we call technical specification, or in general, you can call desired specification. Just imagine, so I say that I want to buy a laptop, okay? And immediately I'm saying that Mayur, can you buy a laptop? Then Mayur will ask that, sir, what for this laptop? Whether you want to play a game or you want to do some simulation. So if it is a simulation, what kind of simulation like that? He's actually like interacting with me, and so our interaction says that okay, I am planning to play a game like Minecraft or probably some kind of uh, very heavy intense game. Then immediately say, oh, you need graphical, you can say high graphic interface. Okay, so then he said that, sir, you need high-end system, probably i7 or i9 with the graphic card is actually like at least 6 GB capability. Like that, he may derive the specification. Okay, and the screen size, everything is actually like bringing it. So now the user, I am the user. I said that I want to buy a laptop. So from there, the Mayur, who's the, you can say the one who's going to buy, he derived the specification, right? So now you put this i7 processor or i9 processor with 6 GB graphic card and 14 you can say inches screen and lightweight, like that he put a desired specification. Then you can see that there is multiple in the, you can say what you call market, right? For example, Dell will have i7 probably multiple edition, and HP will be having multiple editions with graphic card itself. Asus would be there, Acer would be there, like that. Several brands are there, right? So now, which one you want to buy for me? There is a different discussion, right? So the same way, when I say the desired specification, from the desired specification, so what I'm going to end up with some configuration. So the configuration is a laptop with, you can say convertible laptop, okay, with a 14-inch, like that. I am actually like, or Windows based, some kind of configuration I'm bringing it. The same way, based on the desired specification, so I can choose the configuration. For example, here, the robotic assembly, the manipulator configuration I can choose, right? It can be an articulated manipulator. The articulation can be horizontally located, which is one of the popular known is either probably a Delta robot or a SCARA robot. So that means, so I'm choosing the configuration, right? So now, how I set the configuration based on the desired specification, multiple choice, no? The same way, once you choose the robotic configuration, again, multiple choice. Just imagine a Delta robot or a SCARA robot you choose it. The SCARA robot maybe come from 5 lakhs to even 5 crore. Similarly, the Delta robot may be 10 lakhs to probably 1 crore. So that variant is there, and different brands, different way. So how to choose the real system to fulfill the desired task? So then you can see when you go to the real system side. So the real system side, there are multiple things, right? So you need to choose either on shelf. Imagine you are planning to develop your own, then what are the things? You need a mechanical system, the, you can say the structure, which would be mounting the motion system and as well as sensor system, actuator system, control system, right? So indirectly you need a selection of mechanical structure. Then to actuate the selection of mechanical actuator, sorry, mechanical system, you need actuator. And then in order to make a closed loop, you need to choose proper sensor, and certain extent you go, you have to choose, you can say proper control system, peripherals, then algorithm, like that, right? So just for our interest is mechanics, right? So then you need to see that selection of mechanical system would be one fold, then selection of sensor and actuator another fold. From the real system, you can see that these are the two important elements you need to fulfill. But from the task, you have come up with a selection of configuration. But from the real system, you need to select the mechanical, sensor, and actuator, right? So now who will give this information from the configuration to the selection of mechanical, sensor, and actuator selection, right? So this is what we call the system dynamics. The system dynamics is nothing but robot mechanics. So this robot mechanics will give idea to fulfill these two, right? Just for understanding. So imagine, so I ask you to develop a simple pendulum. You all know what is simple pendulum, right? So the simple pendulum is a simple swinging arm, right? But I ask you to fabricate one simple pendulum with my own condition. The condition that the end of the pendulum, it should carry 5 kg bob. Bob means just like a ball, okay? A ball of carrying 5 kg should be at the end of the pendulum. Imagine it's a clock pendulum, imagine, okay? And 1 meter long, and whatever angle I'm saying that angle is supposed to stop. Indirectly, I'm thinking of motorized pendulum. So I want you to develop a motorized pendulum to make sure that so you are fulfilling all those things, right? So now, how will you start? So immediately what you think? Okay, you need 1 meter long and 5 kg at the bob at the end. So other end should be motorized. The motor should be capable of stopping whatever angle which we are setting it. For example, 30° from the vertical, 40° from vertical, like that. If I keep, so I need to stop. So now you can see that even a simple pendulum task. So there are multiple things is coming. One is, so how to choose the proper actuator to stop. right? That is one thing, which is very simple thing, right? So apart from that, you can see there are lots of other complications. What other complication? You will be taking 1 meter long rod, and the rod would be connected with the 5 kg ball. How will you connect? You cannot super glue 5 kg ball, right? You have to actually like properly weld, or you have to revert, or you have to actually like make some fastener, right? And similarly, the 5 kg is supposed to carry by 1 meter long rod. The rod should have proper material, right? And with the proper cross section. So now who will give this information? You need to see. At the end of this rod need to be connected with the motor shaft, right? So how to connect the motor shaft? That is another question. Now the motor is supposed to be mounted on the wall or mounted on the ceiling, whatever. So how will you mount that? Simple C clamp with small rivet is sufficient, or how to choose? Now coming back to the original interest, to stop at particular angle which we are throwing it. So you can see that even a simple pendulum will come with material selection, cross section, you can say connections, which is we call joints, and how to, you can say, actuate, right? How to mount the actuator, everything is coming into a place. Now imagine when we always do a physics, we assume that massless rod, right? When we do a pendulum. So if I consider massless rod, how I will actually come up with a cross section? Can I take a grass straw, which is 1 meter long, cut it and put it with a 5 kg bob? No, right? So then I need to properly choose. So that means you need to actually play your physics or mechanics. So now imagine if I actually consider the bob is concentrated even at the end. Okay, I assume the massless rod. What I can do, I can calculate the force acting at different occasions. The force acting or passing through the rod I can calculate, and I can put a factor of safety of something. Then I see that, okay, this much force is going to act on this cross, you can say the rod. So now in order to fulfill this, so what I supposed to have a cross section. So then you see that there is two conditions, right? If I choose material, I can finalize the cross section, or you choose the cross section and find suitable material to fulfill this. So that means you are actually like playing, you can say one, you keep it, another one you can think it, right? So that is what you call design or synthesis process. So now we are actually going the same way. At the end, you can see that you are connecting with a mounting several times our students or ourselves will not think this. What we always bother, whether the motor is providing a sufficient torque or not, only we'll see, but we'll not bother about the mounting. Imagine I'm taking a bulky manipulator which can carry up to 200 kg. Can I just mount it on a table without any proper fixer, without proper support? No, right? So that means, so I need to see what would be the ground support which is supposed to provide to arrest the adverse motion of the system. For example, now I see the pendulum. The pendulum sufficient motion is only the swinging the arm, right? So now the swinging arm in one direction, what I mounted, but it should not actually like swing the other directions, and the swinging should not actually like topple. That means my support reaction should be proper. So that is where the bigger question comes. So now how to arrest, how to make it. So that is what we call robot mechanics. So or simply we call system dynamics. The system dynamics, if you say, so then what we are indirectly doing it, we are trying to come up with the analytically relating some, you can say, equations, or trying to bring some equations so that I no need to bother about anything before, you can say, develop. So that means I can actually like play with my analytical model and come back, okay, this is what I needed. I fulfill it with a certain factor of safety. Now if I fabricate, the system will work. So that means I need to play in a computational or virtual prototyping. For that, I need a bigger system called mathematical model. So why mathematical model required? We already discuss to understand the behavior, right? To understand the behavior of the system, and then I can actually like design the mechanical control navigation system, right? So that is what we are actually like trying to say. So apart from this, so there is one more also we can use for mathematical model. So for example, you have a system.
evening la 3:30 नंतर Thursday ला.
Ganesh, Ganesh, can you mute?
Friday ला करा मग.
So what is the other one is we can actually like estimate or predict the performance. For example, I am unable to find the velocity. Imagine I am actually like moving in a linear slide. I cannot actually like find the linear velocity without converting anything. Then what I can do, I can use a mathematical model. So for example, I know acceleration or I know position. From there, using mathematical model, I can actually like derive the velocity. So that means I can predict or estimate or identify the parameter. So that also can be useful when I think about the mathematical model. So now you got idea why the mechanics part is important, right? So and why mathematical model is important. So now just for out of your curiosity, okay. So you might have seen the robot called Atlas, right? Or Atlas. So which is the Boston Dynamics, one of the popular you call anthropomorphic humanoid, right? So the Atlas is used to do lots of backflip, you can say stunt and running, jogging, everything, right? So this you would have seen, and you just dig it little serious. So how many engineers are working towards this project? You know any idea? So how many times this robot would have failed? Did you see that? Or how many what you call algorithm they have tested and they failed? Did you check it? No, right? Because we always see the success side, but we rarely see the back end, how much struggle they have done. You know, Boston Dynamics is not a new company, right? It is more than 40-year-old, and they have struggled to come up with this Atlas from single leg biped to now the Atlas. So that much serious effort they have made it. So that means, so you can see that there is a important behind. So that is what we are actually like trying to, we are actually like getting it. Okay, just for our understanding, now you know why mechanics and why mathematical model. So we will actually like go with the same flow. Okay, so we'll actually like go with the same flow, and then we can actually like find it. So I'll just make it to understand. So I hope still you can see my screen, right? Sorry. So this. So nowadays YouTube is very ad based. So I just want to show that you see how the Boston Dynamics Atlas is failing. You can actually like see that even a simple task, it is actually like failing. And these kind of failure, if you are seeing in the beginning, you never actually like appreciate, right? But these all were there in the beginning. Okay. So and what you have seen,
Just
the
a second.
flip or front fold, all those things are actually like only certain small segment. But this is the real part. For making this real part, what you need to know, you need to know the mechanics and how to actually like use the mechanics cleverly. That is what we are trying to bring in this particular short session. So in order to understand this, when I say mechanics, so what I am trying to say that, so robot designed for two things. So one is to manipulate the objects around, or it can actually like mobilize its own, right? Or sometimes it would be mobilize and manipulate together, which is what we call mobile manipulation. But what indirectly we are interested to see robot is the motion. The motion is as per our wish whether the system will go. For example, if I say humanoid, the humanoid walking and mimicking human motion, Or for example, you talk about aerial robot. So the aerial robot fly. For example, underwater robot, it should swim underwater, right? Or even take a mobile robot or leg robot. It's supposed to maneuver in the ground as per your wish, right? In other way around, if we simply say that we are focusing more on the motion. So when you see the motion supposed to be stable. For that, you can see the mechanical structure should give us stability, and then the actuation should provide the required motion. So now, if you focus that, the mechanics supposed to be seen the motion part. So the mechanics can be seen motion part. In that sense, you can see the motion alone you can see, or the cause of motion and motion you can combinedly see. If you see motion alone, which is what we call kinematics, just nothing but study of motion without considering the cause of motion, which is we call the forces and efforts that affect the motion. So what indirectly we are deriving it, we are deriving a relation between the input to output. So in other way around, very simply, the system governing equation we are trying to develop. For example, you have a system. Imagine you give 10 inputs, so it is giving 5, okay, output, and next instant you are giving 20 and it is giving 10, and 30 it is giving 15. So what you can see, you can plot, so 10, 20, 30 in x-axis, and whatever output 5, 10, 15 in the output, and you can actually like bring the relation, right? So now in a simple sense, I have given it is going to be a straight line. So 5, 10, 15 in a way it would be moving with a 10 interval of x. So that means you can get a relation, right? The same way you are trying to bring a geometric relationship that govern the system. So that is what we are interested. So in achieve of this, what we are trying to bring it, we can see that who are all the control. So that control parameter to the system space, which is what you call the variable, can be brought in. So now next instant I want probably 12. So I know that, so the output 10 to 15 is between 20 to 30. So now I see the relation. I see, okay, now if I put 24 or 26, I'll get indirectly, if I put 24, I'll get 12, right? As per the relation. So earlier I said 10 is equivalent to 5, 20 equivalent to 10, and 30 is equivalent to 15 as the output. The input is 10, 20, 30. The output is 5, 10, 15. Now I need output of 12. I can straight away go 24, right? So that is what we are trying to mimic. So here it is a single output, single input. We can easily manipulate, right? But imagine robotic system is a multi-body and it is working in a complex environment. So that means I need to know how to govern and how to control. This is one important thing. So when you go this way, the kinematics you understood, right? The study of motion. But what is robot kinematics or robot kinematics? That you need to know. There are two ways the robot kinematics is described. So if you are talking about manipulator, like the system which I shown, the robot kinematics is actually like described in a geometric level. Okay. But if you talk about mobile robot, aerial robot, or even a legged robot, so then the robot kinematics would be in a velocity level. Okay. So we'll see both. Okay. So now we'll go to robot kinematics or kinematics. So even you just imagine here there is a small industrial manipulator, I put it. So here what would be my manipulator interest? The manipulator interest here, it is probably engraving tool, or you can say probably a end mill cutter is attached with the manipulator. Imagine. So then what would be the focus? So how it would be, you can say, work in the workpiece here, right? So how it is actually like making the profile in this workpiece. So that is what our interest, right? Our interest always on the end. For example, now I am writing on a board. So what would be your interest? So you will not see the chalk, you will not see my individual, you can say, joint motion. You will see always on the board what letter I am writing, and you can say combine of the letter, you are trying to make it a meaningful outcome, or the scribbling would be like a picture, you would take it as a meaningful one, right? Imagine I write randomly one letter here, one letter there, one picture here, one picture another place. So will you able to cope up that way? No, right? For example, I'm saying that just add AAR. I'm writing A is one corner, I is another corner, R is actually like before I. Will you able to read? No, right? So that means you see that you are bothering about only the output which is putting on the board here, which is actually like in the end tool, which is what you call the operating or the task end. This task end is associated with several things. For example, the tool point, tool rotation, tool speed, like that. It is having a set of variables, right? The set of variable I'm making as a single subset or a space. For example, position of the tip, orientation of the tip, like that. I'm actually keeping multiple variable in a single box. This box I'm calling a space. This boxes consist of the operating end variables, right? So then I'm calling it as the operational space. Now, in order to achieve this operational space, what really required? The robot should move the individual motor here, here, all those things, right? For that understanding, I'm showing the same thing, the skeleton. Where are those motors? So these 6 motors are responsible to make it this end effector, which is what you call the operating end in particular position and orientation. So that means when I write A, okay, on the board, my wrist, my elbow, my shoulder should go in certain manner, right? If I'm actually like holding my chalk here and I'm actually like saying that write, I cannot write without moving my joints. So that means even if I see the manipulator without moving these 6 motors, so I cannot actually like reach this particular profile, right? So that means I have to see the robot end, which is we call joints in general, are very generic manner. It is a configuration. So how I configure individual motors, so it would make this orientation or this orientation, right? That means, so the individual joint rotations consist of certain variable set. This set I'm calling as joint space or configuration space. Now you can see that as an engineer, you should map between these two, right? So for achieving this, I need to actuate like this, right? For example, I have a mobile robot in front. So I want to actually like move forward. Okay. So then what I should know? I should know what configuration I have kept it. It is a 2-wheel drive or 4-wheel drive or omni-wheel drive or a bicycle model. So then I can control individual wheel, right? The same way here, I should know like how to control these 6 motor to reach this position, or okay. So if I give random input where my end position would be located. So these mapping I need to know. This mapping what we call robot kinematics. Indirectly mapping between operational space to the configuration space. In manipulator aspect, it is called joint space to task space. That mapping what we call robot kinematics. So here you can see it is in the geometric level, right? So that's why sometimes it is called geometrical model. So now we will go even further. So the configuration space, now you know the input of A1 to A6, right? So whereas the operational space is nothing but the tool tip of the position and orientation of the tool tip. So just imagine that way. So now I know what would be A1 to A6 orientation. I'm trying to see where my position of the tip is located, orientation of the tip located. So then what it is more like a straightforward, right? So I connect the joints with bodies and then I keep it one by one, assemble and see where my tip. So that is what we call forward kinematics. Indirectly, the joint space is known. We are trying to find out where the task is. There is another set. That means I want to reach this particular position and orientation. So what I need to move individual, my body motion. So now for a manipulator, I want to place my, you can say gripper here. For that, what would be my individual joint rotation. So this is something like a reverse, right? So that's why it's called reverse kinematics, or sometimes we call inverse kinematics. So this is more like, you know where you are going to work, what would be your base. From there, base to end, you are operating. So that is where we call inverse kinematics. The forward kinematics, more generally people call assembly mode. So don't get afraid if any paper written assembly mode of the robot manipulator, that is nothing but forward kinematic solutions. Okay. And similarly, the working mode, if any paper you have seen, that is nothing but the inverse kinematics. Okay. So now you got idea what is robot mechanics, what is robot kinematics, and in manipulator, robot kinematics means just the relation between or mapping between configuration space to operational space. So if it is configuration space is known, finding operational space is nothing but robot forward kinematics, whereas operational space is known and you are trying to find out what would be your configuration space, that is more like inverse kinematics. Okay, so now this part is very clear, but you know there is a bigger concern will come if you talk about manipulator. So what bigger concern will come? Just for understanding this, you might have seen several ball, bat, or you can say car, racket games, right? So that you would have seen, for example, ball badminton or shuttlecock, okay, or even a tennis, hockey, cricket, golf, right? So you would have noticed, for example, cricket, hockey probably relatively different games. So just take a golf and cricket. So most of the time, very rarely, for example, Rishabh Pant, Hardik Pandya, Dhoni kind of people can hit six in single hand, right? Otherwise, you can see that most of the player would be holding two arms together to the bat, right? Whereas golf also like that. Whereas you just see badminton, either it's a ball badminton or you can say shuttlecock, you can see that. So that would be always play in one hand, right? Now, coming back to the tennis. So when you go to tennis, you can see that some occasion the player would be keeping the racket with two hand. Sometimes they would be keeping the racket in single hand. So did you notice this? So what really happened? Okay, why this scenario is changing, right? So one thing you would have immediately said that, sir, you see cricket, golf and all, you need more power. So more power will come with both hand. That's why we are doing it. Yes, true. So in tennis, so for example, return shot, or you can see somebody is giving a high speed shot, for returning that to the next court or return back, you need more power. So that's why you are keeping a backhand where it is two hands together. When you are going for a side court where you need more reach, you open your hand. Similarly, badminton, you need reach, right? So that time always you keep single hand. So imagine you are playing a badminton with the two hands together. It's very tough, right? So you will easily lose the game. The same philosophy here, bringing it in a different way. What that means? So I'm trying to classify the manipulator. So you know the manipulator is classified into serial and parallel, right? So now the serial manipulator means from the base to the working end, which is we call end. So base to end connected with bodies in series. For example, you play tennis with you call one arm, forehand shot. So that time you can see that your hand is open. So from your foot to your, or you can say your shoulder to the racket would be open chain. It is serially connected the bodies. Whereas you go with a backhand shot or cricket shot, you can see from your shoulder to your cricket bat or shoulder to your racket would be connected with the two hands. So that means your base is your shoulder and your end is your racket or bat that is connected with more than one chain. So earlier it was an open chain, which is we call serial manipulator. Now it is a closed chain. Indirectly from your shoulder to your bat, two arms are coming, right? So that means it is making a loop. So that's why it's a closed loop or parallel manipulator. Your end to your base parallelly connected with multiple arms, more than one. Whereas if it is a single one, it is a serial manipulator. Now you got idea what is serial and parallel manipulator, right? Why I put this particular question here or discussion here? Because when you talk about forward kinematics, for a serial manipulator, it would be very simple. It's more like I said, no assembly. You take multiple body and multiple joint assembled in a given way. For example, theta 1 is 20 degree, theta 2 is 30 degree, like that. So you take one body, theta 1 is 10 degree, you keep that body in 10 degree angle. Then second body, theta 2 is 30, you assemble 30 degree. Then you are making it very easy. That means the final tool end would be having a single solution. It would be unique. But imagine you take a parallel manipulator. The forward kinematics is not unique, first of all. Okay. For example, you would have studied 4-bar mechanism. So I think the position analysis you would have done. Your crank angle is given. You want to find out what would be your coupler and output angle. So then what you would have done from crank end, you would have taken the coupler length and make a circle. Similarly, from the frame, you take a follower length and make a circle. These two circles will intersect some point. In this case, it would be intersect 2 points. So these are the possible solution. So that means for a given input crank angle, the configuration can be a crossbar or open bar, open chain. So that is where we are actually seeing when you talk about parallel robot, the forward kinematics itself is actually like a complex, whereas a serial, it is a unique. When you come back to inverse kinematics, so both the cases, it would be multiple. Okay. And one more thing also there, very critical. So the inverse kinematics is not, you can say, unique, and it is having multiple solution. And not all the time the inverse kinematics would be in a analytical form. You may end up with numerical form. So for example, you would have started seeing a ROS. I hope you would have seen in the ROS there would be some IK solvers. So IK means inverse kinematic solver. So that inverse kinematic solver usually some search based or optimization based. Why? Because so the analytical relation may not be easily framed when you create URDF, but the numerical solution may be possible. The numerical solution will not give all possible solution. It may lead to one of the closest to solution. So that may not be your interest also. So that you think. So that is one part you might be clear, right? And coming back to the serial manipulator itself. Okay. If the serial manipulator has multiple joints, imagine I have a spatial manipulator, but the spatial manipulator, which means 3D manipulator, the 3D manipulator has more than 6 motors. And these 6 motors are actually like more than 6 motors. They are all actually like uniquely arranged in such a way that it can play in 3-dimensional space. So then you can see more than 6 means. So you see your operational end would be having 3 position and 3 orientation because it's 3-dimensional space. So the degree of freedom is maximum 6, but you have the degree of manipulability is more than 6. So that means you have multiple solution and infinite number of solution. So indirectly you have 2 tasks. Each task supposed to be done by 1 person, but you have 3 or 4 people. So then you can see that. So 2 of them would be idle all the time. All right. So which of the 2 you have multiple choice? So all 4 you can have a choice. One can work. So for example, 1 and 2 work, 3 and 4 can be free. So 2 and 3 can be work, 1 and 4 can be free, right? Like that you have multiple choice. So that means you go more than required degree of freedom, then it is redundancy. The redundancy comes, there would be criticality. The criticality is the inverse kinematic solution is not unique and multiple solution. The inverse kinematic solution is numerical and you may lead into something critical as a singular also. Sometimes your actuator would be drive more power because of this reason maybe. Okay. So that you keep in your eye. So now we'll move forward. So now you are very clear. So robot kinematics means mapping between 2 spaces. So one space we call operational, the other space is task space to what you call configuration space or join space. So now forward kinematics means it determine the configuration of the end effector, which is what we call task space, from the given the join variable. That is what forward kinematics. Whereas inverse kinematics is nothing but for a given desired configuration of the end effector. So what would be my join variable? That is what the idea. So now, if you are clear on these things, we'll go move on. Okay. So what move on? So imagine you want to describe about me. So you can actually describe about me means what way you will describe. I may be talkative, dark skin, short height, long hair, like that, right? But these all descriptions are relative. For example, short height may not be applicable if I go in a Mongolian country. Dark skin may not be applicable if you compare me with other tropical country, right? Long hair, it may not be applicable. For example, you compare with Italy or Korean, right? So that means you need to have some reference to describe one to another. The reference what we call here as a coordinate system. Okay, in order to describe your motion, I need to coordinate from one end to another end, right? So that means I need to bring the some coordinates. From that coordinates, I can actually say that this body is moving with this velocity. This body moved from this point to this point, this much displacement. Like that, I can coordinate. So that means what I need a coordinated system. So now when I say coordinate system, there are multiple ways to coordinate, right? And multiple coordinate system are possible. So you have inertial navigation system, right? So that means you can actually go with inertial coordinate system, right? So the GPS, whatever using, right? So you have a range of the sensor, then latitude, longitude that can be mapped, and then you can say that this is one of the coordinate system, right? Or a spherical coordinate system, or cylindrical coordinate system. Like that you can keep on doing it. But what we are going to use most generally in most of the roboticians uses the Cartesian coordinate system. The name Cartesian came because the person, the Cartesian, developed this particular coordinate system. That's why it's called Cartesian coordinate system. He chosen three mutually perpendicular axes to define where these two intersect, that is the coordinate point, and these three directional, we assume that the axis of the reference, and then we continue. So we usually take it XYZ. You can ask why XYZ, why can't A, B, C, the axis A, B, C also you can choose, no? So there is nothing wrong. So we started using the last three alphabets. So that's the same scenario we are keep on continuing. And again, we are going to use a right hand rule. Why right hand rule? You don't ask, because most of the human being use right hand for every major thing. So that's why they have taken right hand rule. That means you keep, so your thumb finger as x-axis, forefinger as y-axis, your middle finger would be your z, or vice versa. Okay, but you have x, y, z in sequence, so you can find it if two axes are known. That is the idea for the description. So now you got idea. So you need to describe. For describing, you need a coordinate system, which is nothing but what we call references. So now what we are trying to describe. Okay, so what we usually describe, whether it's a mobile robot or manipulator, so there would be initially fixed coordinate system. We call it's inertial system, or simply we call earth fixed coordinate system, to something like a moving body, right? Indirectly, I have two body. I want to have a relation between one body to another in a more comfort way. That is what I'm interested, right? So that is what we have done so far, right? Mapping between two spaces means what? So one space to another space, you want a relation. So indirectly, there are two rooms. So I want to actually like have a communication between these two rooms. The same logic. So here two bodies are there. One body called B, the other body called G. So easy to understand. One is G is ground. So B is, you can say, body, which is moving body or bus, whatever way you can think. So now I want to know the position of the body, okay, with respect to ground, and orientation of the body with respect to ground. So if I know this, I can conveniently play anywhere, right? So now just imagine you are having a very high class car. Imagine you have a Rolls Royce. Okay, the Rolls Royce logo always in the front, right? In the, you can say your bumper or whatever you call the bonnet, right? From there you have the idea here is very straightforward. The logo of the Rolls Royce car, where it is located, I want to know. Okay, from my room. So then what I can do? So I can see where my car is going. From there, I know that from the car, it is 1 meter or 2 meter from my seat or 2 meter from the center of my body. It is located. I always know this, right? So then what I can see, if the point P, okay, the position and orientation of P is known to be, can I find it, the position of P with respect to G? This is what my logic. Yes, this logic we can do. This logic can be done with multiple way. Okay, this is what we are actually like calling the foundation of robot mechanics. So I'll go in that scenario. If you have any question in between, you can actually like ask me now. Otherwise, I will just move on. So it would. Yes.
Yes, sir, I had a question that when there are multiple options, multiple paths in parallel system, shouldn't we use the path of least effort?
That depends. For example, you can go with optimal time, optimal energy, optimal path, indirectly the distance covered, right? So that is depends on your objective. So for example, one point to another point, you want to go the shortest distance you want to take, or the shortest energy consumed you want to take, or the shortest time you want to take. Now imagine there is obstacle. So whether you want to take obstacle free path, then obstacle free path can be multiple choice, which one you want to take, least energy, like that you have, right? So these all depends on your objective. Your objective is just to reach, then you don't need to bother about energy, right? But you say that you need to be optimize the energy, then you will go with the least energy path, right? So these all will come. So it is not only parallel manipulator, even in the inverse kinematics also, like there are multiple options will come. For example, your manipulator rested in one pose. From there, the next position need to go. Okay, the position only known. So now your inverse kinematics is giving 4 solution. Okay, in that one solution is actually like is flipping your end. So then I may not choose that, right? So I will see that with my existing configuration to go as a smooth. So that is what I maybe wanted, right? So like that only I choose. So I'll just check, for example. So this is what, so imagine this is what your current position, and this is the target you want to go. Okay. So then there may be a solution of this. So there may be a solution of like this. So wait, the solution can be, so my pencils. The solution may be like this or like this. So now you can see that if I choose this solution, so it is easy, right? So with the existing configuration itself, I can go. But this solution, if I choose, then you can see that
So you,
my,
excuse me, sir, your screen is not
yes.
visible.
How it is, I shared the screen, right? I'll again share the screen.
Okay, please. Yes, sir.
Yeah. So now you are able to see, right? So now imagine this is the your 2R serial manipulator. So this is the end point which I need to reach from here. So there are two options, right? So there are two solutions may be coming. One solution like this, so other solution like this. So which one you will choose? So from here to here, moving is least, right? But if I choose the solution from my inverse kinematics, there are two solutions. All right. So which solution to be chosen is up to the user. So now imagine you are using inverse kinematic solution using numerical method. So it may lead to this. Okay. If it is a closed form, it will give both. Now you can choose this one is beneficial. You move only like 10 degree from here and then probably 5 degree from here, then it may be making the movement to the required thing. But reaching here, you need to move probably almost 90 degree, and this need to be folded exactly again more than 90 degree. It is much expensive, right? So that is what I told. So you can actually like use it that way. Okay. I hope now you got answer for that, right?
Yes, sir. Thank you.
Yeah. Is there any other question?
No, sir.
Okay, then I'll move on. Okay, so I'll just move on with description, and the next session I will talk about the mechanics and what research I'm doing and all. Right now we'll just focus on this. So when you talk about the description of a motion, so indirectly that is what we are interested, right? So understanding the motion. So that the motion is what we can actually like bring it. So multiple of force. Force means position and orientation. So when you have multiple pose and you synchronize and move it, it's like a motion, right? For example, you take 1 second, the object moved 1 meter to 2 meter. So imagine 1.1 millisecond. So indirectly like 100 millisecond I moved. So then I see that it is pointed 1.2 meter. So 3 meter like that. These all frozen pose. I keep it. Then I actually like sequentially move. Then it is giving a motion. Motion is nothing but so infinite number of position and orientation, right? So that is what I'm trying to say. That means, so when I say pose, so position and orientation. So that's why the camera man says that give a pose. So your position and orientation both are important. Okay. So what we are here interested, you need to describe your position. You have to describe your orientation so that I can actually like map multiple frame, because when you talk about manipulator or when you talk about mobile robot, you are mapping between multiple bodies, right? So that means I need to understand one body to another body, how the coordinate system is relative, so that I can move on, and whenever any information is known, I can bring it back. For that, very important thing is I need to describe the position, I need to describe the orientation. Describing a position is very easy because we are using a Cartesian coordinate, right? So then what I can do, the position I can project to the coordinate system where I want. I project, I can actually get 3 coordinates. For example, this P, okay, I project on this frame G. You can see it is projected here. So it will give this much is the Z-axis displacement. This is the X-axis displacement. This much is Y-axis displacement. So that means that the position of P, I can write as, so X, Y, Z as a simple vector. So that is what we call a description of position in the form of vector. Okay. So that is what we are actually like showing it. So now you can see that the A frame is here and the Q is the vector. So I want to know the position of Q with respect to A. So I can write in the form of simple vector Qx, Qy, Qz. Okay. But when I go for orientation, so imagine there are 2 frames A and B located in the same position, which means same point, but it is oriented apart. So I take 2 duster and actually I keep it in my palm, but I actually like switch one to another in a different direction. So that means what? So these 2 dusters, although the CG is sharing, but the orientation is actually like different. So in this case, how to describe the orientation? So again, we can use the mathematics. So what way we can do? Here we have done the projection of a point to the coordinate system, which is we call frame. We got Qx, Qy, and Qz, right? The same way we can actually like bring it 3 unit vectors in frame B. So the unit vector along with X, call XB unit vector. So YB unit vector, ZB unit vector. So now these 3 unit vectors I can project into the frame A. Okay. So XB projected in A frame means it will give its dot product, right? XB dot with XA, XB dot with YA, XB dot with ZA. So that is what will get it. So then you can see that one projection vector will come, which would be consist of 3 elements. The same way, if I project YB vector to A frame, again 3 coordinates will come. So similarly, ZB I projected in A, so that would be another. So indirectly 3 vectors consist of 3 cross 1. Now can I combine this? Because it's a unit vector, these all orthonormal because XB, YB, ZB are orthonormal, which means orthogonal each other. So that means this projection also orthogonal. So that means you can actually combine these 3. That will give a matrix. This matrix what we call a simple rotation or orientation matrix. So that is what we are trying to describe here in a very simple manner. For example, the A and B frame oriented with respect to x-axis with a phi angle. So you can see that if I projected XB to A frame, that would be unit vector along with the A. So that means XA1, 0, 0. And YA side YB would be cos phi, right? So then this is sin phi. But in X, it would be 0. And YB to ZB, if you go, ZB projected on A along with X 0. Along with Y, it is actually like you can see cos 90 minus phi, that means sin phi, and this is actually like cos phi. So then I can actually get the matrix, so which is what I call rotation matrix. So which would be simple dot product. You can see the XB dot product with XA, XB dot product with YA, XB dot product with ZA. So you will know like dot products. So A dot B, how you can write mod A mod B multiply with the angle between these two vectors cos of that, right? So that is the way you can write. Imagine the angle between A B vector is theta, then what way you can write? So A dot B can be written as mod A multiply with mod B multiply with cos theta, right? Now imagine here what we have taken. So everything is unit vector. That means the absolute value of so XB, XA all would be 1. So what would be remaining? Only the cosine angles would be remaining. So it would be, you can say, simple cosines. So that is what we are going to use it. And this would be simple orthogonal, or you can say a unit vector. This would be orthonormal with this unit vector. This would be orthonormal with this unit vector. That means this vector multiplied with this would be giving 0. Okay. So the dot product would be 0. So this unit vector multiply with this, that dot product also would be 0. Okay. So I'm saying this entire vector. When you take cross product of these two, that would be end up with this. Okay. These two cross product would be end up with this. These two cross product would be ended with this. So but the direction would be changed based on which direction you want to see. That is the way you can actually like think it. So that's why this rotation matrix called so orthogonal matrix, because it is consist of orthonormal unit vectors. So that means the determinant would be unity. Since the determinant is unity, the R inverse would be simple R transpose. So that is the idea. So that is what you call rotation matrix. I hope now the rotation matrix part is done. The rotation matrix can be used many functionality. The 3 main function is one is mapping. So then it can be described one frame to another frame, and it can be used as an operator. Okay. So these all would be the functionality. So now you got idea like what would be the description of a position, what would be the description of orientation. So the description of position would be 3 cross 1. The description of orientation would be 3 cross 3, which is a matrix, earlier is a vector. Now we'll go to the mapping. with this 4th slide, I will stop. So what mapping means? The mathematical relation between, you can say, one set to another set. That is what we call mapping. That's what I said, robot kinematics also mapping. Okay, so now here we are talking about frames. So the frame can be mapped between one frame to another frame in 3 basic ways. It can be pure translation alone, or pure rotation, or general body motion. We'll talk about pure translation. So A and B frame are just translated. So indirectly you can see that. So A frame and B frame, the coordinate system are parallel each other, right? Only it is distance away. That distance is what we are going to call a position vector. So the position vector of B with respect to A is what you call this information. Right now I am choosing a point Q. The information of Q with respect to B is known. That means the position vector of Q with respect to B is known. Can I get it position vector of Q with respect to A? It's very easy. Just vector addition of these two, right? So that is what we got it, right? In the same way, you take a pure translation to pure rotation. So pure rotation, what you can see. So the same idea, the position of Q with respect to B is known. Okay. So here it is, I've written A is known. Imagine A is known. I want to know with respect to B. So what I can do, I can actually like take the rotation matrix of B with respect to A is known, and I can map this relation. Okay. So this way I can actually like a map. If I map this, what I can do, I can go with the general plane motion. So that means I can see that the frame is not only displaced, even oriented. Now again the position of Q with respect to B is known. I want to know with respect to A. So simple vector addition alone will not come, because this Q, position of Q with respect to B is known. So you want to actually like orient with respect to A. So how much? Then you can actually like add. That means, so this position of Q with respect to B need to be modified to the A frame. That means rotation matrix you have to multiply. Then you add the position vector. Okay. So that is what we are trying to do it. You can see that the position vector plus this frame change, because the information of Q with respect to A we need, but B only known that we are converting with respect to A this much, this distance alone. Then we are adding with the B frame how displaced from A. So this is what we call the general body motion. So now you got idea the mapping between these two. Then I said the robot kinematics for what you call the mobile robot kinematics is different. I said, right? What would be different? You can just check. I'll just give a glimpse and then I will close it. So there, the information between body to earth is what important. The earth would be initially fixed. The body frame is actually like moving. The difficulty here is, imagine you take a car, the driving part, okay, and the steering part, what you think, can I say the steering angle with respect to my earth frame? Or can I say that you accelerate with respect to my earth frame this much? Is it more reasonable, logicable? Imagine I have a right turn in front of me. I am driving a car, and you are the cruise Steve, who is actually giving a navigation from the deck, and you are saying that, hey, there is, for me it is 90-degree turn. From your point, it may be 10-degree. Imagine you say that you take a 10-degree turn. Will I succeed? No, right? So that is a bigger problem. And your actuator also like would be with respect to body. Imagine you take a mobile robot. The mobile robot wheels and motors always associated with the mobile base, and always easy to relate with respect to mobile base, right? So that means, so when you talk about mobile robot, the kinematic part, the input velocity command, what we call the wheel velocities, right? The wheel velocity always realizable at instantaneous time with respect to body frame. Whereas I want to know how this body move in a given three-dimensional space, the position and orientation of the body, I want to know, but I don't have the body frame positions. with respect to body frame, because that is not possible, right? What I know, only the instantaneous velocity with respect to body frame I know, I need to map. That means what I need to do, I have to actually like step down the body fixed instantaneous velocity to a position that is not possible. The other side, earth fixed position and orientation of the body is required, but that is in the position domain. I need to elevate to the earth fixed velocity. Okay, time derivative of the generalized coordinate. I can map these two. So that mapping, what we call robot kinematics in mobile robot, that we will see in the next class or next session. But right now, what you understood, the robot mechanics means motion understanding. Right now, we have talked about robot kinematics. Still, we have not talked about the dynamics, because when you design, when you develop a system, you need to know two things: the structural part of the robot and motion part of the robot. The motion part can be brought easily, but the structural part you need to come up with a strong dynamics part that need to be known with the flow. First, we will start with robot mechanics with the kinematics. So the next session we will talk about robot mechanics in a dynamics perspective. Then I will show what is structural dynamics, what is motion dynamics, how you can actually like manipulate, and how to come up with your own design. That way, I'll close it. Right now, I stop here, and so it would be more vague because it is mechanics part. So don't mistake if it is a different talk I can easily give, but mechanics part you can understand only if you are putting into serious concept. Okay. With that, I'm stopping at here. So now over to Mayur, because he said 1 hour, I'm exceeding 1 hour. So I stop here.
Hello.
So, organizer, it is over to
Hello.
you. Yeah.
Okay. Thank you so much, sir, for a wonderful session. Now I request participants, if you are having any queries, kindly put your queries in chat box so that sir can address. Even you can unmute yourself and ask your query.
So there are no questions in the chat box. So you keep the questions tomorrow. Okay, tomorrow I will show more pictures, videos, and all. So then you maybe get motivated towards this particular session. Oh, thank you. So
Okay.
you can always ask questions or email, or tomorrow we can meet. Thank you.
Thank you so much, sir.
So I'll leave the meeting, Mayur and Kanish. Thank you. Bye.
Okay, yes, sir. Okay. Thank
Yeah.
you. Thank you so much. Okay, all participants are requested to fill up the feedback. Link is already shared in chat box. Okay. Thank you so much. All are requested to join the further sessions in time. Thank you.